Okay, let's look at a couple centripetal acceleration problems involving tension. So the first is, let's consider the case where we have an object that we're swinging overhead. So in this case, suppose that we're swinging it fast enough that the tension is almost entirely directed towards the center. In other words, we're going to not worry about gravity. In that case, so notice the object would have velocity, of course, that's tangent to the circle. Um, and its acceleration is pointing towards the center of the circle, centripetal acceleration. And the force that's providing that is the force of tension. So what we can do is we can approach this very much like how we would a Newton's law problem in X and Y. So let's sum the forces in R. So the force that we have in R is going to be the force of tension. And the sum of the forces in R is going to equal the mass times the acceleration in R. And we know that this is going to be equal to v squared over R, so the centripetal acceleration. So this lets us make a connection between the tension force and the velocity and the radius of the circle. So recall the radius of the circle, R. And the thing that I want you to take away from this is this tells us how this behaves. So for example, you could test this too. You could do this experiment. If you were to swing an object on the end of a string, notice as you swing it faster, the tension in the string is going to go up. And maybe you've observed this before. You're swinging something around. The faster that it swings, the larger the tension is going to be in the string. And then also, it depends inversely on the radius that you're swinging around. So if you are swinging something around and you let out string, you make the radius bigger. In that case, the tension is going to go down because it's inversely proportional to the radius. So this is basically, the simplest situation that we can think about in terms of a tension problem, but it gives us an opportunity to look at how this thing behaves. And it's an example that we can play around with at home. We can tie something to the end of a string and whip it around and get a feel for these ideas. Let's look at a problem that's a little more interesting, a little more substantial. And that is the following. Let me paste this problem in here for you. So a bucket of mass 2 kilograms is whirled in a vertical circle of radius 1.1 meters. At the lowest point of its motion, the tension in the rope supporting the bucket is 25 newtons. A, find the speed of the bucket. B, how fast must the bucket move at the top of the circle so that the rope does not go slack? Okay, let's give ourselves a picture here to try and help us figure out what's going on. So we have a bucket. Try and do a better circle. That's, instead of a circle overhead, we have a vertical circle. We have this bucket, and we're interested, both in the lowest point as well as the top. So we have a bucket spinning around in a vertical circle. Kind of two different spots where we're interested in what's going on. The top and the bottom. So, and what else do we know? We know this thing is 2 kilograms. We know, actually, let me use my colors to try and distinguish these. We know that the tension is going to be pointing towards the center in both cases. We know of course, the acceleration is pointing towards the center of the circle as well. And since this is a vertical circle, we're also going to have a force that we neglected or wasn't an issue the last time around, and that's the weight of the bucket. So the force of gravity on the bucket will also be an issue. Okay, so let's look at Newton's second law in R at the bottom. So at the bottom of the swing, what forces are we going to have? Well, we're going to have the tension that's pointing up towards the center of the circle, so that'll be positive. We're also going to have the weight, it's pointing down, so it'll be negative. We know that that's going to equal the mass times the centripetal acceleration. In other words, that'll equal mass times v squared over r. Okay, so we want to find the speed of the bucket. So in other words, we need to solve this thing for v. So we can do that. We'll have the tension minus mg times r over m. And then we would have to take a square root, and that would give us the speed of the bucket. And we can evaluate this. So the radius was 1.1 meters. The mass was 2 kilograms. The tension was 25 newtons minus mg, 2 times 9.8. Take a square root of that thing, and we would find that the speed of the bucket was 1.7 meters per second at the bottom. Okay. So the other question is what's going on at the top? And the question is, how fast does the bucket have to move at the top so that the rope doesn't go slack? So in this situation, what we're interested in is, so now the tension is still positive because it's pointed in this towards the center of the circle in the r direction. But now the force of gravity, the weight of the bucket, is also positive because it's pointed in the same direction. That'll equal mass times centripetal acceleration, m v squared over r again. So in this case, when the rope goes slack, when that happens, that would correspond to the tension going to 0. So when this goes to 0. So when that happens, we can solve this expression for v. So we have mg equals mv squared over r. Notice it's not going to depend on the mass. We solve this for v. We find that this would be the square root of rg. And we can put in our numbers here. 1.1 times 8. Find that this is about 3.3 meters per second. So this would be the minimum speed that you would need to swing this thing around in a vertical circle so that the rope at this speed, this would be the critical speed where the rope would have no tension in it. If you go faster, the rope would have tension at the top. If you go slower, the bucket is going to fall at the top of the circle. So this is the minimum speed to keep the bucket from falling at the top of the circle. And this is sort of a classic problem involving centripetal acceleration. Instead of swinging an object in a plane, a horizontal plane, we turn the plane vertical and we can analyze what happens. So technically this is a little bit different because the speed of the bucket is changing, but it works. We can still do this same analysis. It works good enough.